Hello everyone. This is my second attempt to record this. I recorded it the first time and then the audio was messed up, so I am recording it again in its entirety for a second time. This is a footnote video on ICMR, or Input Common Mode Range. Input Common Mode Range. I wasn't able to answer it on the study hall because I forgot how to do it and I couldn't find my notes on how I was supposed to solve it. So I'm doing it here. And this, I find this pretty important because it's also pretty easy and it's pretty easy to forget. So the simple answer, all you need to remember is that for VCM minimum, you solve this using KVL around VCM. And for VCM maximum, all you have to do is fulfill VDS is greater than or equal to VOV. That's it. So we're going to run through two example circuits. Both of them are slightly different. And I will show you how you can find that. So this is the first one. This is one I actually tried to solve on the study hall. I was not able to. I cut it out because it was like 15 minutes of me staring at a blank wall. Okay, so before we can do anything, we need to split up this circuit into a half range circuit, right? Or a half circuit. Basically, we don't want to solve the whole circuit at once. We only want to solve one half. And remember, we are in common mode. I wrote DC here. Same thing, common mode. So remember the rule about common mode. When you have two circuits that are identical and they share a node, like so, it might as well not exist, right? That node, that empty node connecting them might as well not exist. Now we have a problem that we have this resistor connected to the to ground. How do we get rid of that? We double it up. So recall again, well, I solved this on the study hall, but I'll solve it again for you, right? We could turn this into two resistors. Both of these having 2 times the resistance, right? 2R parallel with 2R is equal to just R. And so we can cut this out and replace it with 2 resistors on each end here. And now we have this unnecessary node in the middle. We can cut that one out. So now we have successfully split the circuit into 2 circuits, individual circuits. And this IC here, this combined current here, these circuits, the one on the left and the one on the right, are identical, right? So the current running through both of these is just 1/2 of IC. Let's write that down here. So I, let me write that in red. I is 1/2 of IC is equal to 0.5 milliamps. Let's redraw the circuit. It gets a little messy. And I'll have to draw more stuff over it, so let's erase that. Na-na-na-na. Ground. Na-na. Ground. This is 2RS, and this is also 2RS, right? Because the initial resistor was just RS. So we've now successfully split this circuit in twain. Okay. So let's do VCM maximum first. Let me just pull up my notes so I know I'm not wandering off from the right path while I solve this for you. So VCM max. VDS is greater than or equal to VOV. How does this help us? Well, we don't know VDS, but we can put it in terms of what we do know. We know everything around VDS, right? This is D, this is S. So let's do some Kirchhoff's voltage law. VDD minus IRD minus VDS minus I to RS is equal to 0. We can isolate for VDS because we know all of these other variables. Meanwhile, for VOV, we don't know VOV, but we know that VOV is GS minus VTN. Do we know GS? Yes, we're given it. Well, in the original study hall, I had to find GS, but that's besides the point. Okay, so now let's substitute all of this back into the initial equation. Move that to the other side. We get VDD minus IRD minus I to RS is greater than or equal to VGS minus VTN. One second. Okay, no, I wasn't mistaken. So we still have this problem that we need to find a minimum value for VCM. But so far, we don't have VCM in this equation, right? Can we get VCM? Yes, we actually can using VGS. Remember that VGS is just VG minus VS. What is VS? VS is going to be this point here. This is S, right? That's going to be the current times the resistance, right? And VG, well, VG is just VCM, right? So now we could substitute that in further, VDD minus IRD. These two cancel out, right? So you end up with IRD greater than VCM minus VTN. Now we isolate for VTN. We get VDD minus IRD plus VTN smaller than or equal to VCM. Now you plug in all the values. VDD is 5. This is 5 minus 0.5 milli. 5K plus 0.7. And you're left with 3.2 is greater than or equal to VCM. Or VCM is smaller than that, right? So that's our maximum value. VCM max is equal to 3.2 volts. How about our minimum? Well, we can do Kirchhoff's voltage law around this loop. To make this a bit more understandable, we're going to make VCM into an actual voltage source. I color that in red so you know that that's just sort of part of my thing. And now we can do Kirchhoff's voltage law on this, right? So what's Kirchhoff's voltage law here? We have VCM. It goes through VCM. And now it comes across here minus VGS. And it goes down minus I to RS. And it comes back around. That's it, right? Is equals 0. Let me pull that down here so we have some more space to work with. VI minimum. Now, we have VGS, but we don't actually need to get rid of VGS, do we? Because we can just, well, let me see, 1 second. Okay, so I'm wrong. We do need VGS. That's why I put that into the question. Now, VGS is not provided within the question, but you can calculate that yourself, right? It's just DC analysis. So, if you actually substitute VGS the same way we did earlier, everything will cancel out. So, not a good idea. So, we can move that over to the other side, and we'll get VCM is equal to VGS plus I to RS. So VCM is going to be 1.33 plus 0.5 milli times 2000. You do the math. 2.33. And in fact, the first part of this question, that is the answer, right? The first part of this question, the initial question, asked us to find VDC, VCM, so that the whole system works. And I simply found the minimum DC value. That's fine. Okay. So that's an example of the VCM max, VCM minimum. How about this example here? This is slightly different. The major difference here is just this southern part here. Instead of being a resistor, we've replaced it with a current source. So let us find VCM max. Remember, same thing. VDS is greater than or equal to V overdrive. Okay. What does that mean? Well, we could substitute VDS the exact same way we did the initial time, right? So VDD minus IRD minus VDS minus, well, actually, we'll keep it there. We'll keep it there for now. That can be simplified to plus VS. Wait, can it? 1 second. Okay, sorry. We solved this a little differently because we don't actually know what VCS here. We know it has a minimum value, but that doesn't really work out here. But in this case, if we do minus VS, or we know that this is VG in and of itself, right? Because that just finds a position here, right? It's VDD minus IRD. You get, sorry, not G, D. Keep messing up the letters. Now we can add VS on both sides. Minus VS. And now we get VDS, right? Because this is D, VD, and that's VS. VD minus VS, VDS. And then obviously we can substitute in VOV is equal VGS minus VT. Let's put that in. So we get VDD minus, or actually, let's just expand this a little bit further. What is VGS? VGS is, actually, sorry, we don't expand VGS. Not yet, not yet. We expand VS here, actually, and you'll see why in a second. VS is VCM minus VGS, right? It's the same process as before. VCM minus VGS is VS. And now these two VGSs cancel out, right? So now we can write in VDD minus IRD minus VCM is equal to negative VT. And now we have VCM in. Remember, the goal starting from this is to put everything in 1, variables you know, and 2, VCM. You need VCM. Okay, so now knowing that, you can isolate for VCM. Move everything around, you'll eventually get VDD minus IRD plus VT. Oh, sorry, this should be, it should be greater than or equal to, sorry. And we have all of these values, right? We have I combined. Once again, we need to find I, which is just 0.2 milliamps, because these are identical parts. They provide an identical amount of current. So it's half of the combined current. And if you put all of that in with all of these values you see here, VCM is smaller than or equal to 1.5 volts. That's your maximum. Now, once again, let's do our minimum. It's going to be this loop here, which is going to be VCM minus VGS minus VCS minimum, because that's the smallest value this can be. Usually we wouldn't know what VCS is, but we're trying to aim for the minimum possible value, right? So VCS minimum 0.4. And then we end in negative VSS. So this would actually be a voltage source like so. We exit out the positive end, so we add here is equal 0. So we isolate for VCM as always. It's going to be VGS plus VCS minimum minus VSS. Oops. Substitute in all the values. We already know them. Negative 0.28. Actually, ooh, we're not given VGS, are we? Sorry, let me just pull that up. Sorry, VGS is equal to 0.816. There you go. Now you know how to solve that. So I hope that clears up how to do ICMR, input common mode range. Exactly. Yeah, awesome. Have a great day, everyone. Hope this helps.